doesn't bind up all the glucose and keep it to itself, like the muscle does, because the Km in the muscle is very low. Right? So muscle is never going to take its glucose and happily give it away to somebody else. Okay. So we can appreciate, there's a transporter in here that equilibrates the glucose. We mentioned that before. We can appreciate that this is regulation of different isozymes. So maybe the muscle isozyme, I have no idea, but let's say there's out of 200 or 300 amino acids, 10 of them are different, and that's enough to make the Km for glucose be different by 100-fold. While the catalysis is still good in both cases, right? So you're not mutating the catalytic triad. You just got some changes in the structure around the binding site probably, which contribute to the Km difference. So this is regulation based on, what's the affinity enzyme for the substrate, how much substrate is there, where are you in the body or in the cell, and so it's just working that way. Now there's also a regulatory binding phenomenon here. So here we're in the liver, and so here we've got fructose 6-phosphate enhancing inhibition and glucose relieving it. So what this means here is that if there's a lot of glucose around, hexokinase will come out of the nucleus and function in glycolysis. This would be a way to actually use some of the glucose in the cell. So here we have an equilibration of hexokinase. So there's a way to get it through the nucleus, and when it's in the nucleus, it's bound to this regulatory protein, so it's kind of kept in there. So maybe this regulatory protein, we don't really have the details, but it might help it get across the membrane in some way or something like that. But this is regulation by sequestration, right? And fructose 6-phosphate keeps more of the glucose in the nucleus. It's not really clear why it should be fructose 6-phosphate that's doing this, but fructose 6-phosphate could be a signal that enough hexokinase has already been, enough glucose has already been converted because it's downstream, right? So that if there's a lot of that around, then it's kind of like saying, oh, we've done enough glycolysis, let's move you back into the nucleus. But if there's more glucose than fructose 6-phosphate, well, let's come out. So it's that kind of thing. So that's an example of a different type of regulation, clearly sequestration of the enzyme in a different cellular compartment, but then also modulation of that sequestration by the metabolites that are involved, right, in a way that hopefully makes some sense as far as what the liver cell is doing. Questions? So this is one of our three, right, in glycolysis? Yeah?
So what would the concentration of glucose need to be for the hexokinase to come out of the nucleus?
Pretty high. I don't know exactly how high.
Okay.
But
the 5 millimole was.
But probably, this is an approximate concentration that you want to keep in the bloodstream.
Okay.
And so if it gets much above, this is an equilibrator. So whatever's in the liver cell is going to reflect the bloodstream pretty accurately. So if it starts getting 6, 7, 8, something like that, that's going to be enough to pull it out. So there's a sensitivity of this interaction to the glucose that helps break that up. So glucose is the substrate. So it could be that the substrate binding is enough to break up that regulatory protein interaction. Does that make sense? So PFK1. Here's the reaction. Fructose 6-phosphate ATP. So it's a committed glycolytic, first committed glycolytic step. F16BP is the product. ADP is the product. So ATP is the substrate, but ATP is also binding at an allosteric site. Okay? And when ATP binds at an allosteric site, the effect of it is, here's the activity, here's the fructose 6-phosphate concentration. Right? So this is a sigmoidal enzyme. You can see the sigmoidal plot. So it's a regulatory enzyme. But you can see what happened with high ATP. The K, not the Km now, right, but the K0.5 Vmax. Right? The K0.5 Vmax is a lot higher when there's a lot of ATP. So the activity is clearly knocked down by having a lot of ATP around. And the way it's knocked down is by decreasing the affinity for the other substrate. Okay. So it makes sense that you want to knock it down, because if there's a lot of ATP already, you don't want to run glycolysis, do you? I mean, the cell is full of ATP as it is, and the point of glycolysis is to oxidize glucose so that you make even more. Right? So you're in a happy state. You can run the other. You can go back up, store your energy in glycogen. So similarly, if you have a low energy signal, so AMP and ADP are low energy signals, clearly. Right? If there's a lot of ATP around, then there's going to be not so much AMP. If there's not much ATP, there's going to be a lot of AMP. So if there's a lot, as the green triangles mean a lot, then you activate it, because it means there's not much ATP. So clearly these guys are competing for the allosteric site somewhere else. That's the most likely scenario. We have inhibition by citrate. Citrate, you know, is in the TCA cycle, and high levels of citrate signal a highly energy-rich state for the cell. It means the TCA cycle is more active, things are churning through it, and the consequence of that is the citrate level is higher. You could ask, well, why citrate? Why not use isocitrate? I have no idea, but the idea is just that some TCA cycle metabolite is a signal. And then we have this other thing here, fructose 2,6-bisphosphate, which I will come back to in a few minutes. It's a different metabolite that we haven't talked about yet. Okay? So PFK1. Question?
So to use a crude metaphor, it's something like we've got, when we're in the TCA cycle, we're at high gear. We're churning out energy, we have a high energy state, we have a signal from citrate, we want to ignore it, take the foot off the gas.
We want to use citrate as a signal that it's time to take the foot off the gas. And the way we're going to do that is to have citrate
Expressed, and that's going to be expressed quantitatively by a higher K 0.05 Vmax.
Yeah, if citrate works the same way that ATP does. Okay. And I'm not sure about that. Okay. You know, it may turn that things down to the level of the actual Vmax level more than K. Like this curve could be shifted out. You know, not so much, but it could look more like this, so that this level is always low, and not be as sharply, you know, not so much compromise the shape of the sigmoid. Remember we talked about that when we talked about allosteric enzymes. It's like affecting the Vmax or the Km if it were my Kale-Smith enzyme.
So when we were talking like a few minutes ago about how PFK1 is always being regulated though, because you want to keep ATP concentration high, correct? Like when,
yes.
Okay, so then is it ever on that low ATP side, or is it always being regulated? Like
Yeah. So obviously, yeah. So it's always being regulated. It's always, you know, if you had, you know, if you went to 0 ATP, it might be like way up here somewhere, right? If you went 0 ATP in the regulatory site. But yeah, so this is kind of qualitatively showing low versus high and trying to rationalize in terms of the energy state of the cell and what the enzyme is doing. But yeah, so that idea has to be combined with the notion that it's never really functioning at a super high level.
And then at some point, is there just, to turn it off all the way, is that curve just shifted so far to the right that nothing happens? When you want to turn glycolysis off?
That depends on the level of this guy. You know, if it shifts far enough so that the level of this guy can never really get up into a reasonable activity range, then that will be enough to do it. Yeah. Okay. So here's pyruvate kinase, which is step 10. So the third one. This one's more complicated. So first there's allostery in regulating it in the same way that we've just been talking about it. So acetyl-CoA is also a measure of high energy. Some of these things you just kind of have to know. Like, it makes sense because it's downstream, but you don't know which downstream one. So I'm saying